All right, methods of preparing amines. How do we synthesize them? So this is a review. One way you can do it is to use a cyano group as your source of nitrogen and then reduce it. Okay, so we know LAH is a reducing agent that works on cyano groups or cyanides. So we take cyanide as a nucleophile, and this is an SN2 reaction. And then once we get cyanide on there, we just reduce it. And we just have to remember that this adds a carbon to our chain. So this carbon gets added on. So if you're looking for synthesizing with an extra carbon and then an amine, cyanide is your way to go. Cyanide's your guy, okay, your reagent. If you have a carboxylic acid and you want to turn it into an amine, you might want to go through an amide and then reduce the amide. Okay, so we have a carboxylic acid, turn it into an amide by changing this to Cl, and that makes it into more reactive acyl chloride, remember, chapter 20. Then your ammonia comes in, and we can displace the chlorine. Okay, my pen's not working again. All right, so once we get the amine here, or the amide, then we can reduce the C double bond O. It can go away with excess lithium aluminum hydride. All right, electrophilic aromatic substitution and reduction. You learned how to nitrate this, so you put a NO2 group on here. And then once you have that group, then you can reduce it. So you just turn the O's into H's with probably hydrogenation is the easiest reagent to remember, but also many of these metal catalysts can reduce hydrogen on there with acid, in the presence of acid as your source of hydrogen. Okay, so maybe just be familiar. Whenever I see metals, I think reduction because they're really good reducing agents. So whenever I think of reduction, I think of hydrogen. All right, so hopefully that might help you a little bit. When I see oxygen, I think of oxidation. So like KMNO4, OSO4, CrO4, CrO3. When you see a lot of oxygen, it's the opposite. And then our last reaction on this page is alkylation. Like we were saying at the beginning of this lesson, that you have nitrogen with a lone pair. Just like it can attack hydrogen, it can also attack carbon. So carbon electrophiles. So when you do that, though, notice that you can deprotonate the hydrogens, get the lone pair back. But what happens is once you have the lone pair and you're neutral, you can continue to do further alkylations. So I could, if I had excess ammonia, like excess methyl iodide, I could keep going and I could get it to the point where it has multiple CH3 groups. And it turns into what we call a quaternary salt. So that means it's going to have, iodide could be the counter ion. But basically you've added on 4 alkyl groups here because that lone pair will just keep attacking the CH3 groups. So you end up with what we call a quaternary ammonium salt. That's a nitrogen with 4 groups, so like quarter, or, this is means 4. So you have a counter ion, and so that's why we call it a salt. Okay, here azide synthesis, and azide is N3 minus 1 charge. And azide is actually what's in airbags. Azide can break down into nitrogen gas, and that's the gas that provides that inflates the airbags. So azide, you can just think of it like cyanide in terms of it being some kind of anion that attacks here and then displaces here. So it's like an SN2 kind of reaction. And we have an N3 group here. And then with the N3, we can reduce that. It's very similar to like this kind of reaction here. You can just reduce it, or like this LAH can reduce it as well. Okay, so that's reduction. So all these reactions, a lot of these reactions involve reduction. So you have some kind of oxidized nitrogen group getting turned into a reduced nitrogen group. Oxidized, reduced. Okay, oxidized, reduced. See that? So it's very common. And then we threw in alkylation. All right. And notice you're keeping one nitrogen, so the other nitrogen leaves, probably is nitrogen gas. How would you synthesize these amines from the reactions above? So let's just take, for example, this first one. How would I synthesize that using this reaction with cyanide? Okay, cyanide followed by lithium aluminum hydride. So one thing I could do is start with one less carbon. So this is maybe where my cyanide comes in. So I'm going to have 1, 2, 3 carbons, and then some kind of an alkyl, like halogen, like Br, or any kind of leaving group like iodine, bromide. Those are good ones. And then I could do step 1. I could do cyanide or sodium cyanide. And then step 2 would be like lithium aluminum hydride followed by water. Okay, and that's going to give me my amine right here. All right, so that's one way I can do it. All right, so let's say for this one we have benzene ring, and I want to show how maybe I can use a carboxylic acid to start, just for variety. Okay, so if I have a carboxylic acid, maybe I can turn that into an amide and then reduce the amide. So step 1 could be SOCl2, thionyl chloride, make the acyl chloride, so this OH turns into Cl, and then that makes it more reactive for an amine, so like ammonia. Okay, and then once I have ammonia, I make an amide, so C double bond O, NH2. And then I want to reduce and get rid of this C double bond O, so I can do that with LAH. Okay, and I want to use excess LAH because I need to get rid of this C double bond O. Okay, so once I have LAH, then I can work this up with water. All right, so that is an example of this reaction up here. So step 1, 2, 3, and 4. So do you know why they say excess NH3 here? Is because when the first NH3 comes on, this is going to turn into a positive charge. So you need another NH3 to come and deprotonate it so that it becomes an H2. All right, so it helps to say that here, excess there. And we need excess LAH because an amide is more oxidized than like an aldehyde or ketone. So we need more than one equivalent to reduce it. And then this last one, you can pick any of the other syntheses. We could pick the azide synthesis. We can't do this one because we need a benzene ring to do that one. This is to make aniline. So aniline is a good common name to know. That's aniline. Let's see. We could do this one, but again, this one's problematic because it's hard to control it so that it doesn't do multiple alkylations. So let's do the azide synthesis. For the azide synthesis, I'm going to use my SN2 reaction. So I'll put a halogen here. I'll do sodium as azide, NaN3. Step 2 will be to reduce it. So I'll use LAH. Okay, and that's this reaction here. LAH followed by water, or you could do H2 on platinum as well. That's fine. Now let's talk about the problem with this multiple alkylation right here. So multiple alkylations makes it hard to control so that you get one R group on there. So there is a way to avoid that. And it's what this synthesis is for, is the Gabriel synthesis. This one's really great for primary amines specifically. So this one's actually with the secondary one, but this is great for synthesizing primary amines as well. The way that this works is we use this compound called phthalimide. Okay, I'm sorry, my pen's not working. And phthalimide acts as a kind of source of nitrogen here. Okay, but notice the nitrogen's already tied up by the rest of this molecule, so it's not going to be able to do multiple alkylations because of that. So our first step is that the hydroxide takes the hydrogen and makes this nitrogen into a nucleophile. And once our nitrogen is nucleophilic, now we can do an SN2 reaction on here. It's better if this alkyl halide is primary, because then the SN2 reaction will be faster. But it will work on the secondary as well. So this will attack here. And then once it attacks there, then you end up with the amine. You could sort of see that right here. Here's my amine. And I just need to hydrolyze it from this phthalimide starting material. That's what the acid is for, is hydrolysis. Notice this is like an amide, and this is also an amide. So if you remember back a couple chapters, this would get activated. So these carbonyl groups can get activated, and the water could attack. Okay, so H2O can come in and attack here. And eventually I could get it so that OH groups will be here and this will be freed up. Okay, so thinking back to that mechanism, let's draw it out. So this carbonyl gets protonated, and then water can come in and attack. Okay, so far I'm showing water attacking here, and then I need to do some proton transfers, because remember the idea is that water is adding and nitrogen is leaving. So I need to protonate nitrogen. I'm going to have the water deprotonated, and then since the water is going to stick around, here it is, I need to show it here. Now this group is ready to leave, so at this point I can show either one of these hydroxyls coming in, and it's going to let go of this amine group. So now the amine's only tethered by this side, and the same thing happens on this side as this. So this will get protonated, water will attack, and I'll be able to hydrolyze both sides of it. Okay, so my end result is I'm going to end up with phthalimide turning into this byproduct here, phthalic acid. Okay, so this is right here. And so with both of those hydrolyzed off, I now have my amine freed up. Okay. All right. So that's the Gabriel synthesis, and why that's useful is that we were able to monoalkylate just by having the nitrogen tied up here. It could only react once, and then it gets released. Okay. Usually the synthesis is written this way, starting with phthalimide, KOH, alkyl halide, and acid work up for the hydrolysis. Okay, and that's how you get your amine. So using Gabriel synthesis, how would you make each of the following? So I would start with phthalic acid. So it helps to practice drawing this. Okay, it's basically like this. And once you have that, our first step is KOH to deprotonate this molecule. Our second step is to figure out what alkyl halide we need. We need an alkyl halide like that. So I need a carbon group and then a halogen right here. And then our third step is to hydrolyze the amine from the phthalimide, right? So I have this R group attached, and then I need to hydrolyze it away. So that's what the acid is for. All right, and that will make our product, which is this guy. All right, so practice going through that, and notice all of these are primary amines. So it's a great way of making primary amine. Now, another way you can make amines is by using an imine or an enamine. So we have an imine here, and you can reduce the imine using hydrogen and platinum. Along those lines, if you want to do a one-pot reaction, which means mix everything together, instead of doing two separate steps like this, you could do what we call sodium cyanoborohydride reduction. So this is like sodium borohydride is NaBH4. If you put a CN instead of an H, you get cyanoborohydride. Okay, and this is to make the imine, and then this is to do the reduction. And I remember when I was an undergrad, this is one of the first reactions that I did in the lab, was I was watching some grad students do it, and they were checking their fingernails because they apparently, like, your fingertips will start turning blue if you get cyanide poisoning. So it's like, oh my gosh, what am I getting into here? So anyway, so that's what they did. So how could you use reductive amination, so amine, so making an amine, for this transformation? So the idea is we want to use one of these two pathways, reductive amination, And first I need to open up this molecule, but I don't have any functional groups. So think back to Chem 262. Remember we made alkanes reactive by brominating them. So you could brominate them selectively at the tertiary carbon. And then we can do like an elimination. So maybe we could make that into a double bond. And then the idea would be maybe cleaving here and opening that up. Okay. So if we open that up, maybe we can make aldehydes or ketones or carboxylic acids. And you'd have to sort of decide. I think what we want to do is use ketones or aldehydes, and that way we can do the imine, which can be reduced to the amine. Okay, so to do that, we get aldehyde or ketone, and then we do our reductive amination right here. Okay, okay, so I'm going to do an imine, but then those imines can get reduced, so I'm just going to get rid of the pi bonds. All right, now once I have that, notice this methyl group is this methyl group. And then last thing I need to do is get methyl groups onto these nitrogens, right? So the problem here is if I do CH3I excess, I'm actually not going to be able to stop it at just 2 methyl groups on the N. The N will keep going and make a quaternary salt. Remember, it'll just keep attacking the methyl groups. So I'm going to have to think of another way to do that. That is up here, I could have the amine, instead of being NH2, I could have methyl groups already on there. So maybe instead of this step here, get rid of that. Maybe when I think back to this step, I can maybe add the nitrogens with methyl groups already by simply using an dimethylamine here, an H+, and sodium cyanoborohydride as my reducing agent to get rid of the pi bonds or to add hydrogens to them. Okay? All right, so then that is the product. So let's go back and fill in the reagents. So can you guys do that? We got Br2 or NBS also works, and heat or light. Here I'm going to do an elimination with hydroxide and sodium hydroxide and heat. This step is going to be ozonolysis, so O3, followed by zinc in water to get my aldehyde or ketones. And then step 4 is going to be reductive amination. Okay, so step 1, 2, 3, 4, and this is step 5. 5-step reaction. All right, and this is the new stuff right here.